Welcome back for part 3 and the final part on the video about RF power monitors or samplers. The two previous videos should be watched prior to this video, and links to those videos are provided in the description area below the video. At the end of part 2, I posed the question as to whether the current sampler circuit was really what we wanted, even if the current sampler performed perfectly. And let's quickly examine the three types of samplers and see what I meant by that comment. The Sim-Smith diagram here shows something I've done in the past, which is make use of the isolation block, which lets you have a generator and a load and have other generators and other loads in a Sim-Smith simulation. In this case, we clone the generator, so this generator, which is a 1500 watt generator of use Z0 type, is the same in both of these. For a load, we do not want this load to be used. What we want is we want the load right here to be used. And the reason for that is I'm going to change the resistance here manually. We're going to sweep the length of transmission line here, and we will obtain all the impedances represented by a certain SWR. I want to use that load for this block and this block also. And the way I do that, and both of these are the same, the way I do that is by not cloning the load here. I clone the generator, but for the load I use the ohms part is the real part of the impedance seen right here, T1.Z, and the imaginary part of the impedance is the imaginary part of T1.Z. So doing that makes this block, this impedance right here, and this impedance right here exactly the same as this impedance right here. Now I have three circuits. These three circuits are the three circuits I wish to compare. The first circuit is a power sampler. And this is the bridge circuit that was in the tandem match article originally, and it's kind of gotten the name of tandem match, but it's a two transformer SWR bridge, basically, a two transformer forward and reflected power bridge. Whoops. This circuit is the current sampler we used in part 2, and this circuit right here is the resistive voltage sampler that we used in part 1. All three of these circuits are built right now in Sim-Smith to provide 40 dB of coupling, minus 40 dB of coupling. So if we look at the output here, the first thing I'm going to look at is the power into T1. The power into T1 will vary based on, these circuits are lossless basically. The power in T1 will vary based on the impedance here for a UZ0 type of a generator, and will be 1500 watts for when I use X match. But right now, I've got a 2-to-1 SWR. Let's go back to a 1-to-1 SWR for a moment. And we see that the power actually being delivered into this point right here is 1500 watts. Now let's see what this sampler, and this sampler all report. This sampler reports this power. And I plotted these by basically taking the power in the resistor that I want to use, which is R1 here. Look at the power and then multiply it by 10,000. 10,000 is 40 dB. I did the same thing for the current sampler and the resistor and the resistive sampler too. For the second circuit, the current sampler, the power it reports is also 1500 watts, and the resistive sampler also reports 1500 watts. Everybody's good and giving the right answer. Now let's come along and change the SWR. Let's change this SWR to 2-to-1 and look what happens. The power in the load, which is this blue trace into T1, has dropped from 1500 watts to 1330 watts. That is what we saw before. It is mismatch loss for a use Z0 type generator with a 2-to-1 SWR. It represents just a little bit, it represents 0.51 dB. If we went to a 3-to-1 SWR, it would be 1.25 dB. Nevertheless, what we do here, we're seeing some interesting results. We're seeing the power sampler here reporting the forward power in the circuit, which is still 1500 watts. It does not report the net power, it reports the forward power. The net power would be obtained by taking this circuit, subtracting the value we got over here, and that would give us the 1330 watts. But what it reports is the forward power. The current sampler reports a power that ranges anywhere from about 378 watts to about 3.37 kilowatts. That's a huge variation. And it reports the low power where the resistance is high. It reports the high power where the resistance is low and consequently the current is high. The voltage sampler does exactly the inverse of that. But the problem is these guys are reporting wildly different results. You may not care about that if you're just looking at a waveform and you can just adjust the the range on your oscilloscope or whatever. But if you want this to remain constant, clearly the power sampler is a better choice. The power sampler is actually interesting in that it reports the same power even if the SWR out here is something other than 1-to-1. We can change the SWR to be different values, and we can say that the current and voltage samplers would be probably tolerable to use. Well, 55 ohms is a 1.1-to-1 SWR. At a 1.1-to-1 SWR, a 1500 watt signal will be reported as 1.65 kilowatts or basically 36 kilowatts. It's basically a 10% error due to the SWR. That really isn't a 10% error. That's just what it reports. Remember, the current sampler is reporting 40 dB less than what the actual current is. The voltage sampler is reporting 40 dB less than what the actual voltage is at that point in the line. If we change the generator type to be a X match, we don't see a lot of difference here at the moment. As we raise the SWRs up, go back to a 3-to-1 SWR again. We see that the number rose from 3-point-something kilowatts to 4. The X-match generator is almost exactly the same as a UZ0 when the load is close to the 50 ohm number, but when it's quite a ways away from that, the X-match generator has a mathematical match in it which delivers the full 1500 watts. And that's why we see the power being delivered into T1 now is 1500 watts. Turns out that the power sampler actually reports a forward power of 2 kilowatts. And that is exactly what the forward power is in here. In a 3-to-1 SWR, the forward power is this. The reverse power is 1/4 of what the forward power is. 1500 minus 500, 2000 minus 500, which is 1/4 of 2000, is 1500 for the net power. The first power sampler we're going to look at is the Bruni coupler. And the schematic here shows what most people would recognize as an SWR bridge. The two resistors down here are generally replaced with a diode to rectify this voltage, capacitor to hold the voltage, and some kind of resistor after the capacitor to bleed it down. And then those voltages either go to amplifiers or they go directly to some sensitive meter. This circuit can be built with a lot of different parameters. I chose to build it with 10 turn winding, 5 on this side, 5 on that side. When I did this, I had to adjust the C2 relative to the number of turns. And you can see in SimSmith this works out so cool. I mean, here's adjusting C2. You can see the V sub R is plotted just like it was plotted before. And again, these SimSmith files will be available. When I get all 3 videos done, I will make one big zip file that has all the files I used in all three of the videos. I plotted the voltages just like I did before. And we can see here that as we change the capacitance value, with the 50 ohm, let's make it exactly 50 ohm load. And let's adjust this capacitor for minimum value here. That's pretty good. And then the resistor that we have, which has already been adjusted, needs to be adjusted to compensate for the inductance in the transformer here. And we can set its value. That's pretty good. And what we notice are a couple things here. That with a 50 ohm load, we see a pretty flat frequency response down to a little below 2 megahertz where it starts to roll off. That's due to an inadequate amount of inductance in this circuit. However, as I add more inductance, I start to have other problems. So it's always a trade-off. And this circuit is pretty broadbanded as it is. I find that these resistors, though, unfortunately have to be very, very high. Look what happens. They're set at 1 mega ohm right now. Look what happens as we drop the resistance values down. As we start to drop them down to something that's even halfway close to being something we could drive 50 ohms with, the low frequency end of this just goes away. If we want to drive 50 ohms with these resistors, we have to have so much attenuation that what's left is a coupling factor of maybe minus 60 dB or so, which makes this circuit not very useful. Most people may have made the comment over the years, and rightfully so, that this circuit is really nice, but it's only meant to drive high impedance loads. And with that being the case, and I agree with that, this circuit really doesn't represent what I was looking for a coupler. But again, the file will be available. Play with it to your heart's content. It's kind of fun to play with these things. You can learn a lot by just using SimSmith to vary the values, and you might find something that's better. Again, I challenge anybody who has a circuit that they think would do what I wanted to do and do it better. Please let me know. I will be glad to include it. I'll build it, modify it, play with it, and either do a video on what's right or wrong with it, or if it's better, it would help everybody. It would help everybody in the community. But as far as I'm concerned, unless I'm willing to put active components in my power sampler, this circuit is not a good circuit. And finally, let's look at the power coupler that is used in the tandem match circuit that was originally running QST. I believe this circuit probably has other names too. I don't know what they all are, but most people end up calling it the tandem match circuit. And it's comprised of 2 transformers. Each transformer has 1 turn winding on here and here, and multiple turn windings on the other side. So this represents one transformer, L1, L2, and L3 and L4 represent another transformer. This circuit has no other parts beside those 2 transformers, and an input and an output power, and a sampled input and output power port. And these resistors right here are really outside of the unit. They're in the equipment under test. And if you aren't using the reflected power, you basically would put you'd either put an internal 50 ohm load to ground on it, or you'd put an external terminator on the coax connector. So let's look at this circuit in a little more detail. It has a transformer here which samples the current. It has a transformer here which, from this point right here to ground, is looking at the voltage. So this one looks at the voltage, this one looks at the current, and they're combined in such a manner that we get forward power right here, and we get reverse or reflected power right here. So if we look at this circuit with a 50 ohm load, this piece of transmission line, let's set the length to 0, so it's 34.88, it's the same length as 0, it's a half wavelength, but it's 0, so we have 50 ohms right here. And let's also look at the SWR. So this circuit has an SWR, and it's a pretty high SWR at the low end. And it's high at the low end for the simple reason that there's not enough inductance here to make the circuit really, really high impedance. This circuit right here, let's change it to 22. What I built was a circuit with 22 turns. To get a 40 dB coupling factor, this needs to be a factor of, needs to have 100 turns on it. At 100 turns, we can see that we have 0.15 watts here out of 1500, which is 40 dB down. And with that many turns, of course, the SWR is very, very good down here. However, this circuit cannot be built very nicely. This circuit is shown as being very simple, but in reality, 100 turns on an inductor here, this is going to have a resonant frequency. It's going to be quite low, down probably in the 5 megahertz range or so, or even lower. And there's stray capacitances. The stray capacitances we saw before and how they affected the current sampler will affect this circuit also. I am not including them in this. Analysis right now because we included them kind of ad nauseum, I guess, in the previous circuit. And if you want to analyze this circuit, you can certainly put a capacitor here to here, and here to here, and then figure out what's going on, like I did before. But bottom line is running the shield of the current of the coax through the center turn, through this one turn right here. Leaving it open on this side and connecting this side to ground gives you better performance than just running a bare wire through it. And that's what I built in my circuit too. But when I was trying to get this circuit to be broadbanded, I ended up having to put fewer turns in the inductor. Now, fewer turns means that the inductor saturates quicker. It saturates quicker, which means this can see less voltage here. Consequently, it handles less power. But nevertheless, this is what I built, and I measured it. And I got numbers as to what power it can handle and everything else. But we see an SWR curve like this, and this is not really that bad. I mean, it rises at 1.8 megahertz. It's somewhere in the order of 1.15 to 1. And let's see, we got to get this circuit back down here to get the. Okay, there's our forward voltage or forward power, sorry, and our reverse power. The for given turns ratio in this circuit, which I have right now set to be 22, and a 0.99 coefficient of coupling, the performance of this circuit down here is probably pretty typical of what you'd actually build. Up here, it's not going to be quite right, but let's dispense with that for the moment, and it needs to be compensated for just like the previous current sampler did. But there's some other things going on with this circuit that are kind of interesting, and it's true of the other power circuit, the Bruni circuit also. And that is, if we set the SWR here to say a 3-to-1 SWR, and we sweep the length of the transmission line from 0 to half a wavelength, we see that right here we have a very nice 3-to-1 SWR. However, over on this side, you see what's very typical of an SWR circuit a lot of times, and that is that this curve on the other side is not quite the same 3-to-1 SWR. And that causes us some errors in our circuit, but not really that much. This is a pretty good match. A lot of SWR bridges have a big discrepancy, but this circuit actually works quite nicely. So I measured the circuit, left SimSmith for a while, went and drug out some equipment and made some measurements of the circuit. And the circuit I built looks like this. It's two FT82-61 material cores. So they're 0.82 inches in diameter, and they're 61 material, mu of 125. And as you can see, one side of the center conductor couples to the other transformer, and the other side has the shield here, and it's got a small piece of 0.141 inch Teflon solid dielectric hard line going through here. So this, I figured, was about as good as I could build a circuit. And the performance is pretty good. If you measure the circuits through gain, so that's taking the input and output port, and it's symmetrical on both sides, taking the input and output port, and we see the gain from 1 megahertz to 100 megahertz goes from, I don't know, at 1.8 megahertz it's 0.02 dB down, and at 50 megahertz it's 0.05 dB down. I mean, it's incredibly flat. If we look at the SWR of the through circuit, we see pretty much what we saw before on the graph. SWR runs from about 1. It's actually a little better than what SimSmith predicted. Because at 1.8 megahertz here, it's less than 1.2. That may be due to the fact that these toroids don't have a mu of 125. They may have mu of 130 or something like that. The permeability of toroids is usually pretty, for ferrite material, is not very accurate. It's plus or minus like 20%. Nevertheless, this is the SWR I get in the circuit, which is quite good. And this is the directivity. Directivity is putting power in one direction through the bridge and having a perfect termination on the output and seeing what difference the two powers are on the coupled ports. And when the directivity is very, very, very large, that means the circuit did a very good job of getting all the power, all the forward power to the forward port. This is the coupling, 26.9, 26.9, 26.9 dB. So it couples very, very flat. The directivity here is 10, 20, maybe 20 dB here at 1 megahertz. It's in the 30 dB range down here, and it drops up, and it starts dropping down up here too. However, that means we'll get the reflected power incorrect, but the forward power is still quite accurate. So this circuit was actually better than I expected it to be. And when I put power into the circuit, 200 watts produced a core temperature, and it produces it not in the current transformer, but in the voltage transformer. And these little terminators are shown to be the coupled ports, and this is where I put the power in on these ports. The transformer that samples voltage was at 53 degrees Celsius. At 100 watts, it was at 21 degrees Celsius temperature rise. And that's with a 1-to-1 SWR, of course. So this circuit could handle pretty easily 100 watts at about a 3-to-1 SWR with not any trouble. It certainly won't make it to a kilowatt. I put 600 watts into it for about 5 seconds, and it got noticeably hot. Hot to the point where when I put my hand over the top of this enclosure, I could feel the warmth coming up. So it can't handle high power. But nevertheless, this circuit is a pretty good circuit to use on the output of a 100-watt transceiver. And that brings me to the final point here. Another type of RF sampler that I have not mentioned in this video so far is the high-power attenuator. And 4 high-power attenuators are shown in this picture. These two are 100-watt ones. This is a 200 or 300-watt one, and this is a 2,000-watt one that's oil-filled. If we notice a couple things about these attenuators, all of them are marked with an input. They are not symmetrical. Even though the resistors inside of these things are symmetrical resistance in terms of values, the one resistor on the input side, particularly for attenuations greater than a couple dB, sees the bulk of the power. And consequently, that resistor is a large resistor. So in the case of this resistor, in the case of this attenuator right here, the resistor on the input here occupies most of the space in here, and then the other resistors are there's a piece of transmission line that goes around it. This one's all done on a flat surface inside, but the other resistors are considerably smaller. That means that if you accidentally apply the power in the wrong direction, you will immediately blow up the resistor on the output side. However, if you buy attenuators like this at a swap fest, a lot of times the markings are removed from them. And notice there's 4 shown here, but 3 of them have a female in connector on them, and 1 of them is a male in connector. I've got about 12 or 13 of these things, and it's split in terms of which connector is the input connector. Most of the time they're female. About 2/3 of the time they're female, and about 1/3 of the time they're male. But without knowing via marking which one is the input, you're in deep trouble and you're just guessing. So anyways, we can analyze these in SimSmith quite easily. And what I did in SimSmith here is I have a circuit where I basically replicated the generator and the load so that I can have 2 circuits side by side. One is a T attenuator, one is a pi attenuator. They're done in ruse blocks. I've shown this formula before. This formula comes from various websites and out of textbooks. But nevertheless, what you get here is an identical attenuation. So if we look at this attenuator, these are both 30 dB attenuators right now. In the case of the T attenuator, we see a 46 ohm resistor, almost a 47 ohm resistor here, a 3 ohm resistor here, and a 47. In this case, for the pi attenuator, we see 53 ohms, 790 ohms, and 53 ohms. However, if we look at these from a terminal point of view, from the resistance, say from this pin to ground, or from this pin to this pin, or this pin to ground, which is the only three ways you can measure this device, we see exactly the same results. And I'll show that just in a minute here. However, if we look at the power here, let's set these at 30 dB just for grins for the moment, which they are. 1500 watts is being applied to these attenuators. And in the case of the T attenuator, I calculate power for three different, calculate power for all 6 resistors. It's part A, resistors 1, 2, and 3, the power I calculate, and part B, resistors 1, 2, and 3 for the power. And what I see here, move this over just a little bit, what I see here is resistor R1, which is on the far side of the T attenuator, has very little power in it. Resistor R2 has, I don't know, a little bit, maybe 70 or 80 watts in it. And resistor R3, which is on the input side, has over 1400 watts. We can take this scale here and, okay, so this resistor R2 has about 90 watts in it, and resistor R3 has just 1.5 watts in it or something like that. And if we look at the resistors in the pi network, even though they're different values, they're put in a different place. They have exactly the same power dissipation. So the first resistor has the same power. So R1 in this circuit has the same power in it as R2 in this circuit does. R2, same thing again. R3, same thing again. Very, very, very interesting. Years ago, I figured that out, and I thought that was like the coolest thing. But nevertheless, this is the way attenuators work. And if we were to go and I wrote a little Excel spreadsheet here, which calculates the values for various dB attenuations, and assuming they're all 50 ohm input impedance, I calculated the resistors again, which is the same values I get in SimSmith. But I calculated the resistance from the center pin to ground, and the resistance from the center pin to center pin. So there's 2 center pins to ground, one on each side of the attenuator. If we look at the 2 different attenuator schemes, the T attenuator and the pi attenuator, we get the same values. If you go to a swap fest sometime and someone is trying to sell you a 30 dB attenuator, I'd take my ohm meter, and you need an ohm meter with enough, a high enough quality ohm meter that you can zero out the lead length. But I'd measure the input to ground. Both of them should measure just a little over 50 ohms, and from center pin to center pin, they should measure 93.8 ohms. If they don't do that and one of the sides is less, probably that attenuator got put in backwards and somebody blew it up. That doesn't remove its value as far as being a dummy load, but it certainly makes it not an attenuator anymore. So I have I have this table in my cell phone if I'm at a swap fest and there's some attenuators there that I think I might be interested in. Anyways, I thought you might find that interesting. And in conclusion, there really is no one best solution for everyone. I hope I've done a reasonable job of explaining the choices and showing how to model these circuits. If you like these types of videos, please subscribe to this channel. Also, please click the like button for videos that you do like. If you do subscribe and would like to be notified when I produce a new video, click on the bell. Thank you again.